So slope fields. All right, back up for guys. Sorry. So slope fields, they're also called vector fields or direction fields. So it's basically just a way to visualize what our solution is to a differential equation. So this is kind of our intro to differential equations, which we'll be doing next class. Yes, I think it's next class. So basically the idea is that we don't know what our original graph looks like. Now obviously here we're able to say original graph. But the idea is that we don't know what our original graph looks like, but we do have a bunch of little tangent line slopes. And when we graph all those little slopes, we can get an idea of what the original graph looks like. Okay, so it's basically a tool for us to find a solution to our differential equation. So here, obviously, we have the graph that's drawn for us, and this is just a small representation of slope field. So the idea is that we have a bunch of little points in which we draw the little tangent lines for. So if I were to draw my tangent line here, I would go on forever and then continue. So these are just like little snapshots of our tangent lines. Okay? And these are, we have just a few drawn in. We're going to be drawing a lot of them. But the idea is that having all these little tangent lines, we can then kind of see the curve of our graph. So I'm going to just go ahead and dive straight into our graph. So what we're doing is just really drawing a bunch of little slopes. So the idea is that they give us our derivative, and we're trying to get a picture of what the original function looks like. Now, on the AP exam, they don't give you this chart. They would give you this, and then they would give you this guy here. And on the AP exam, they don't make you draw all these little ones. They usually have, they make you do like 9 or 12 of them. But we're going to do more of them so you can get a better picture, a better idea of what the picture looks like. So really, all we're doing is we're just going to be graphing little tangent lines all over our chart here. So they tell us our derivative is y. So that means I can go to the point, let's just start off at 3, negative 3. What is my derivative at the point 3, negative 3? So I take this point, 3, negative 3, and plug it in. What is my derivative at 3, negative 3? Negative 3, good. It's equal to y, so it's my y value. So I'm going to go to the point, 1, 2, 3, negative 3. So here's my point. And then I'm going to go ahead and just do a little tiny chunk of a slope of negative 3. Because again, this is my derivative. So derivative is talking about the slope of the tangent line. So at that point, 3, negative 3, my slope, whatever my original graph was, if I were to do a little picture of what my slope was, that's what we're going to draw. Now, we're just going to do a little chunk of it. And to kind of help you out with this, the slope of negative 3, if we were back in algebra 1, we were doing the slope of negative 3, we would count up 1, 2, 3 over 1, and then we would connect these, right? Now, we're not drawing a big long slope, we just want a little snapshot of it. So I'm just going to, that's what I use to help me when I'm drawing my slopes, is I just think, okay, I want to aim for that as if it were going to go through. I'm not drawing that whole big long slope because I want just a little bit of it. But when I'm drawing my slopes, I'm aiming for that point there. So I'm just going to draw my little slope of 3. And it's negative, so that's where we're in that direction. Okay, so then we move on to the next point. 2, negative 3. What's my slope there at this point? Negative 3. So again, I'm aiming for this point over here. So a slope of 1, 2, 3 over 1. So I'm just going to draw a little snapshot of negative. And then again, what's my slope at 1, negative 3? Negative 3. So again, I'm aiming for this point up here. And there's a little snapshot of slope negative 3. What is it going to be for all of these? The same. Why is it negative 3 for this entire row? Yeah, it's just our y value. So if my y value is negative 3, then it's going to be a negative 3 for all these. All right, let's just go ahead and on our negative 3s. All right, so then we're just going to continue this process for each of these points. All right, so let's go ahead and do our next one. So we've got this one here. So our point 3, negative 2. So we're not at this point. What's my slope? Negative 2. So now I'm aiming for a slope of up 2 over 1. So I'm aiming for that guy. So it's going to be a little less steep. And then would you guys agree that it's going to be negative 2 for all of these? Are we okay with that? It's just for one of them. Okay, so negative 2, negative 2, negative 2. And again, I'm aiming for that other point that would have been on our line. Okay, so then our next one, so we've got the point 3, negative 1. So 3, negative 1. Now we're looking at this point. Would just be, when we plug it in, negative 1. So again, now my slope is a little less steep. And so that's going to, once again, be the same for this whole row. Now, we don't always have that it's the same for the whole row. It just happens to be for this particular. Okay. So then, as we continue down, what about when my y is 0? What are all my slopes going to be? 0. What does a 0 slope look like again? What kind of line? Horizontal line. Those are the best ones to use. Are you using
Yeah, I wasn't your pencil. I don't know where it went.
I don't have your favorite pencil. I do have a pencil you can borrow. Okay, there's something about that favorite pencil. It makes a big difference. Okay, so then as we continue on down, I'm just going to keep it right here. So for the 0.31, we have a slope of 1. So again, we're aiming for that other point. So this is just 1 all the way across. Okay, and then at the 0.32, it's going to be 2 all the way across. Okay, I'm going to go, let's see, it's down to over 1, so I'm going to be aiming for that. And after 3, we have a slope of 3. So again, I'm aiming 1, 2, 3. Okay, so this kind of gives us the idea of what our family of parent graphs would look like. So this is our derivative. We were just simply graphing a bunch of little tangent line derivatives. Now, if you think about it, when we have a derivative, so let's just go back to, I'm going to pause this for a moment. Let's say that my derivative was equal to just x. Let's go for x. All right. What would my original function be? Actually, let's make it nicer. Let's make it a little nicer. If my derivative was 4x, what would my original function be? 2x squared plus c, right? So we would have integrated, and then we would have gotten that our derivative was 2x squared plus c. What does this plus c mean for us? It's a constant. Now, depending upon what this is, for this particular graph, we know this is a parabola that's been stretched vertically. But what would that plus c do to our graph? What would that do to our graph? Oh, just move it up or down, right? So really what we have is that for my derivative being 4x, the parent function could be this, or it could be this one, or it could be this one. It could be any of these, right? These are a family of functions. It could have been any of those parabolas. So that plus c is any of these. Once we have that, once we figure out what this exact c is, maybe it's 2x squared, maybe our c is 3. Then we know it's the exact one that's at 1, 2, 3. Then we know it's exactly this parabola here. So this is what we call the particular solution. This is, and then the plus c is the general solution. So the general solution is our family of possible functions. Our particular solution is the exact one that satisfies that initial condition. So what we have here on our slope fields then is that we're basically able to see the general picture of our possible original functions. And later, next class, what we're going to do is we'll actually solve for the particular one. But today we're going to look at what does the particular one look like that goes to the point 1, 1. So here we have all the possible ones. We can kind of see the flow here goes like this, and it goes like that. So now they're asking, find the particular solution that goes to the point 1, 1. So let's take a look at our point 1, 1. Let me pick a color. Okay, so I'm going to go to the point 1, 1. And it's asking us, what does our graph look like at that point, basically? So we're, instead of having all of our family functions, we're now stopping it at that point 1, 1. So probably the easiest way to think of this is think of it as a ping pong ball putting it in water. So our slope fields kind of look like the current or the flow of water. If I were to throw my ping pong ball in here, where would the current take it? So if we kind of look to the right, following my current, would you guys agree that my ping pong ball would probably go something like this? Following that current, it's going up steeper and steeper. Are you guys okay with that? Okay.
Wait, is the current going to the left or the right?
Well, now we're also going to check what does it do to the left. So we're going to go both ways. So now if I go to the left, would you guys agree that it's going to kind of bottom out here because we see the current's flat there? Does that make sense? Okay, so I put the ping pong ball in water, and we're basically saying what would the path be that it would take. So this is our particular solution that goes through that 0.11. This is what our exact, not exact because we're doing approximate, but this is what our original function would be that has a derivative of y and has the initial condition of the 0.1. So our slope field is again just all those little dashes, and then they'll ask us sometimes for the particular, to draw the particular solution that's literally just drawn in our graph following that. So our particular solution, I'm just going to write it here. What is this? Is this purple? Does that look like purple to you guys?
Yeah.
Okay, so the purple line is our particular solution to the 0.11. Okay. So then, instead of doing point negative to 0, let's do point. To the point negative 2, negative 2. Okay, so let's say instead of asking us for the particular solution for the 0.11, let's take a look at the particular solution to the point negative 2, negative 2. So negative 2, negative 2. So we're looking at this point right here. Okay. So again, drop the ping pong ball in. Where does the current take it? So would you guys agree that it would look something like this? Now, again, this is kind of bottoming out here. So our orange line is our particular solution that goes to the point negative 2, negative 2. So again, you're just pretty much following that current. If you're not sure, if this doesn't help out, if this is kind of confusing to you, what you can think is just, okay, for this one I had my slope pointing me down this way, so just kind of direct it down until you hit another slope. Here, my slope, if I were to go up, it's pointing me towards this. Oh, now my slope goes a little bit steeper, so now let's match that, and then it's going to now go to the slope of 0, so we're going to have to kind of match that. So we're just kind of connecting our slopes, if you will. Kind of the idea here. You could have gone a little more extreme where you kind of connected here, and then gone up with that. So if you want to, you can think of it as kind of connecting the slopes. So again, your line is your particular solution, just the dash marks is your slope. Now, we could find a particular solution for all of these individual points. Usually on the AP exam, they only ask you to do one particular solution. And again, they usually only have you do a smaller portion of your slope field. So this is it. This is all that we're doing. So it's really just drawing a bunch of little slopes. And then when it asks for the particular solution, then you draw that line. Questions with this?
It doesn't have to be exact, right?
No, so you're just going to have approximate. Now, if you had this and you're like, oh, obviously that's a problem because that doesn't follow the current at all whatsoever. But it should approximately follow the current. Also on AP, they're not going to get out a little ruler and make sure you actually hit a slope of -3. What they're looking is that your slope of -3 is steeper than your slope of -2. Okay, and that your slope of 1 looks like a slope of 1, not like a slope of 2 or something like that. So it doesn't have to be exact, just again, little snapshots. So really the way that people lose points on slope fields is that they just calculate their slope. Yes, ma'am.
How would they ask you a question like this if you test?
So it's very possible that it could be a multiple choice and that they have you do some type of math, or they would ask which slope field would go with this differential equation here. So they'd be not matching, but they would give you the slope fields. Or they might give you the slope field and then say, okay, which of these derivatives matches up with that? On for response, if they were to have it, then they basically would give you kind of a smaller snapshot of this and just say, fill in the slope field for these 9 points. And then probably part B would be to draw the particular solution. Part C then is going to be solving the differential equation, which we'll do next class, which is almost always 6 points of the whole problem. So if they were just for response, there'd be like the part A, part B, small portion of it. It'd be great if they had like 20 of these on the test, right? Usually it's only a couple. All right. Are there other questions so far? Okay, so let's take a look at our second one here. Now over here, our derivative is 1 over x. So as I do slope fields, I kind of like to look for patterns. Obviously, you can see the space upon x. So if x were 0, what would we know about our slope? Undefined. Now we're used to drawing slopes undefined as a vertical line. We won't be drawing vertical lines, just leave it blank. And then can we get our slope here to be 0? Is it possible for 1 over x to be 0? No, so you're not going to see yourself. Okay, I want you guys to go and start filling in too, so you can. Again, you don't have to fill in the chart. It's there to help you out. It's there to help you out if you want it. And as you can see, our derivative or our little slopes are going to be based upon x more so than y, since x controls it. You wouldn't go through, you would head toward up like it would be up. It's just an undefined slope. You think of it as a vertical line, but technically you don't draw that. But you would still think of that as you're drawing in your particular solution. Okay, so hopefully your slope field looks something like this. Do we agree? You should see kind of shallower slopes as we go to the left and right. Now again, for undefined slope, we don't actually draw anything. We can think of it though as a vertical line, but we don't actually draw the vertical line. So now I want to find the solution going through this point. Alright, so the point 1, 1. So again, we can think of vertical lines, so when we draw to the left, it is going to head down like that. When I go to the right, again, you can think of it as, okay, I'm going to just continue on the slope of 1 until I hit the next little dash mark, and I'm going to adjust my slope. Alright, and then let's go through the point, -2, -1. What's our particular solution? Questions with that? Feeling good? Really doesn't get too crazy. Okay, let's go take a look at our next one. So now we have a couple where you actually have to consider both x and y. So again, just look at patterns. I like to consider when they're each individually 0, how does that impact your slope fields? When they're the same value, how does that impact slope fields, things like that. So let's just start off with when x is 0, what's my derivative going to be? 0. So I know that's going to be 0 for all of this. So when x is 0, so that's this here, and I'm going to have a slope of 0. What's that? Oh, thank you. Not at 0, 0. At 0, 0, we have that undefined. Okay, and so then let's take us into the when y is equal to 0. Would you guys agree we would have undefined? So we know that that's going to be a vertical line. So again, we don't draw anything with it. All right. What about when x and y are the same values? What's my slope? What's my derivative? -1, right? When x and y are both the same, so when they're both, like, so 1, 1. I take 1, 1, put it in, I get a slope of -1, right? So the point 2, 2 is slope of -1, -1, -1, -1. So I'm thinking just when x and y are the same values, then I get a slope of -1. Again, over here, -1. That looks a little too steep. Okay. What about when they're the same value but opposite sides? Then what would it be? Like here. So the point 3, -3. When I put that into my derivative, what do I get? 1. What about the point 2, -2? 1. Alright, so then when they're the same value but opposite signs, then I have a slope of +1. And then I'll let you guys continue from there. Go ahead and finish filling in your slope field. Oh, I did that wrong. I did -1, didn't I? Woo! I was like, hold on a second, that doesn't look right. Let me try that again. See? It's those little mistakes that get you the points wrong on the test. Okay. So now go through. You might be able to kind of visualize what's happening. But now go ahead and go through and fill in the rest of your slope field again. Only fill in the chart if you want to or whatever pieces you need to.
Or you can follow the overall pattern.
Just make sure you are getting the pattern correct. What's that?
Don't basically don't answer. It's like a typhoon.
Like a roller coaster kind of.
question before that. You said maybe wrong.
It's a little easier if you go for when y is 1 and y is -1. That would have been smart to start off.
Circle. What?
Nailed it.
Why do you guys underestimate them?
It's Margaret.
Yeah.
You know, whenever Colton does something cool, he's like, nailed it. On The Bachelor.
Oh, I was like, am I supposed to know who Colton is? I don't have a student named Colton.
I'll bring a picture for you.
Hey.
We'll put it on the wall.
Thank you.
I'll do that in Stinger. That's coming out.
I'm glad you said something about singers. So guys, this has nothing to do with what you're talking about. So we're going to be talking about our cross-section project soon. This lovely guy.
Wait, we don't have to.
I know, next week. So ideally next class we're going to get the instructions for this, and then the following senior will be kind of a work day for it.
Is it a group project?
No, sorry.
Just the third quarter.
Yes. Right? Yes. Okay. All right. Sorry. Let me finish this up here. Okay. So ideally, you got something that looks approximately like this. Again, on the AP exam, they don't have you do as many dots, but we're just doing more so we can get a better idea of the picture there. Okay, so Garrett already alluded to what our solution is going to look like. But we can see it looks like a circle that's kind of expanded out a typhoon, I think he said. So we've got the point 1, 1. So again, as you see, you kind of go around.
Circle.
Woohoo! Okay, I didn't do that quite as, that's not a good read. I gotta redo that, I'm sorry. It's a little better. That's not as good either.
For the most part, it's
Okay.
gonna follow a pattern, right? It's not.
Yeah. Right, no, it should follow pattern because we're just having, our parent function is just getting repeated through vertical translations. Yeah, so we should have, now obviously our ones that we did before, depending upon where you are in the graph, like obviously this looks different than this because of where we're located, but we should see that all these ones on top kind of have that same general idea, and all these ones on the bottom same general idea. All right, so then the point -2, 0. So again, we're going to have approximately this one.
Oh,
All right, questions with that? So now 4 is a little different. It still considers both x and y, but we're not multiplying or dividing, we're adding. All right, so again, go ahead and do number 4. Just a general sketch of it. You know what? No, let's not do number 4. These take forever. Let's do our matching. Let's take a look at our matching. Okay, so here it says match each slope field with the correct differential equation. Guys, if you want to see number 4, it's on the notes on that one. But so here are multiple choice. We've got our derivative functions. And so you're going to try to match it up with which slope field goes with it. So I want you guys to go and give this a try. Again, think through what we've talked about. There are specific values that could make it a little bit easier for you. You can always test points as well, but you're going to match up your derivative with the slope field graph. Oh yes, I'm sorry.
On the last one, like there's some that were undefined. Like, does it matter when you draw it to the
No. So, it's especially for the circles, we can't connect that. Because it's not that it's at that point our slope is undefined, but the graph itself is not undefined. Does that make sense? The derivative is undefined, but the graph itself is not. So I'll see what it is. Yeah, and it's good. So our is the rational one. Yeah, it's just one. It's just what it is. I try to do one because. So. Okay. So no back there. It's really good. Once you get your possible matches, check with, let's put 2 people around you. Feel free to work with those around you as well.
It's hurting my head. Fucking 0. Wait, it is. Because he caused himself cutting my It could go either way. There's no experiment.
Okay, 5 is D, I think.
This would be a line.
Yeah, because I plugged in 1, 1, and the only one that I went for is D.
If it were.
At 1, 1, the slope is 0.
Oh, yeah.
Okay, Barcelona.
So I guess you like look at specific things.
I think what you have to find the word 0 is
Yeah. So yeah, it's easy. It's 7.
8, 6 is D.
Okay. So as we went through to do this, what did we do to kind of help us decide which graph was what? Plug in 0, 0, okay. And if we look at 0, 0, they all end up being the same value, 0, 0, or 0, don't they?
Plug in on.
How about, I heard 1, 1?
Yeah.
That's a, oh wait, oh, you know what? That's not 1, 1. Where's 1? It's like 0. Okay, so we can see that the 0.11 is a little different there. Okay, so if we take 1, 1 and put it in, so let's see, what do we get for A? 2. So which of these has a slope of approximately 2? Not this guy, right? Maybe here. Yeah. Maybe there. Maybe there. So we know this is not A. Okay. What about if X was 0? If X was 0, what's my slope going to be for A?
0.
0. So which of these has a slope of 0 for all X's being 0? 6. So you want to think X zeros are Y, so X zeros right here. All these are zeros. So that lets us know immediately A. I like to kind of start off with zeros. I don't know, I feel like it's a little bit easier. How about C? So when Y is 0. So when Y is 0, our overall derivative is 0. Does that help us out? So that would mean our horizontal axis would be 0.
100%.
Number 8, right? So this would be C. Now, what are these tick marks here? Why are those ones vertical? Yeah, that's just the markings on our axis. Those aren't actually our slope. So let's check those. Which one? What'd you say? 5 is D. How did you know that 5 is D?
When you plug in 1 and 1, you get 0.
Right. So when our x and y values are the same, you get 0, 0. Also, too, they have differing points at 1, 1. So this would be D, and then that leaves B for number 7. And again, you can always take points and test it to make sure that it's actually true. But yeah, so kind of look, there are a couple of things maybe consider where the 0 or undefined, but then also to look for points that are different on the slope fields and then test those. Okay, let's go take a look at our next one. Alright, so again, kind of same idea here. So we've got 4 different graphs. Go ahead and match it up with your differential equation. And then once you complete your matching, you're going to do number 13 and 14, where you're just simply doing the particular solution. So they've already drawn the slope field for you. Here's some particular solution. Alright, what did we get for number 9? E. Okay, I agree with that. Alright, what did we get for number 10? B. Awesome. 11? Good, and then 12 would be... Good. Alright, do you have any questions on this? I like them actually. Okay, so then here we're just drawing our particular solutions. So, here they've already done our slope field, they've already drawn the particular solution through 0, 1. So sketch solution curve through the point 0, 2. Should look pretty similar. Okay, so you see that parallel. And sketch the solution curve through the point 0, negative 1. Okay. Questions with that? Okay. And then we've got through the point 0, 1. Okay, so again, we can kind of see that it bottoms out and then goes up against this, and then going to the right, it goes steeper. So again, if you're thinking of like connecting the slopes, I have a slope of 1, and then steeper slope here. It's going to kind of go along that path. And then we have the point negative 3, 0. So negative 1, 2, 3, 0. So it's kind of a waterfall. Again, we're going down because of the steeper. Nothing too exciting. Okay. So really that's the basics for slope fields. Now we are going to move on to our derivative of the inverse, but part of your homework is to finish slope fields, but whenever it asks you to draw a slope field, it takes forever, right? So let's just do the odds of drawing the slope fields. But if it's like a matching, if it doesn't ask you to draw the slope field, it's like here where you're just drawing the particular solution, actually do all those. If it's a matching, I think there's a matching thing for you. Also do this. So if you're drawing the slope field, let's just do odds. I mean, you could do the evens if you so desire, but I want you doing slope fields for 5 hours. Okay, so now we're going to transition to our derivative of the inverse of a function. Okay, this time actually. Or you still have about 5 more minutes. What's that? Odds when it asks you to draw a slope field. But if it's like just draws a particular solution or matching, it actually do that. But when it's like the long process of doing all the little dashes. Thank you. Oh, just Alright, so we're going to do that in the notes.
No, what's supposed to be under that?
Yeah, where is it? That's why I stopped listening to the meteorologists. Okay, so our second piece is the derivative of the inverse of the function. This really isn't difficult in task, it's just you need to memorize our formula. I will also show you, either today or during Stinger, how to derive this. Should you forget it, you can actually derive it pretty quick. But if you memorize your formula, you don't have to worry about that. So what this is they ask us to find the derivative of the inverse of a function. Now, obviously, if we're given a function, we can just simply find the inverse. You can first find the inverse and then do the derivative. That's not difficult. But sometimes it's not so easy to do that. So obviously, for our first example here, we could just find the inverse of x squared. How do we find inverses? Good, switch x and y. So switch x and y, solve for y, do your derivative, or when you switch x and y, you could just do an implicit differentiation and find your derivative that way. Also, too, though, sometimes they don't give us the actual function. They just give us a chart of values. So you have to be able to remember your formula for it. So if you have the function and you don't remember your formula, you can just do the inverse, do implicit differentiation, and find the derivative that way. But when they give us a chart of values, that would not be so easy to do. So the basic process is that we need, actually let's talk about this up here. So this is our formula. And so again, this is saying the derivative of the inverse of our function. Now let's talk about this here. So this is f prime, that's just our derivative, like normal. Derivative of f of x. But our y, this here, right, so this is the y value of the point on f inverse of x. Okay. So this is the y value on the point of f inverse of x. Okay, so we're actually just going to go and dive into an example with this. This is showing you the implicit differentiation. Yeah, okay, that's a good example. Okay, so it says, here's our function, find the derivative of the inverse at the point x equal 9. So every single time we do this, we're going to write original and inverse.
Wait, was there a
Yes. Oh, I'm sorry. This is the y value of the point on the inverse. Or sorry, on the inverse. It's the y value of the point on the inverse. So every time we do this, we're going to just start off by labeling our points. Our point on our original function and our point on our inverse. And again, what we're plugging into our formula is going to be that y value of our inverse. I'm just going to put a box for it. I'm going to rewrite my formula here so we can refer to it a little easier. And our derivative of our inverse is just 1 over the derivative evaluated at our inverse. And again, this is the y value of your inverse value. So I need the y value of my inverse to plug it into my derivative. Another way you might see this notation, this looks kind of funny, but instead of saying d dx of f inverse, would be f inverse prime, right? So that just kind of looks weird though, because it's an inverse and prime, so I'm going to write it like this. But that's just another notation for it. Okay, so it says find the derivative of our inverse at x equal to 9. Yes, Chelsea.
So like you take you get your inverse and you take the derivative, plug in your x, and then you put that 1 over that. So
Wait, hold on. Say it again. So which said again?
So like your original equation, you have to like find your inverse, and then you take the derivative, and then you plug in your x value, and then it's 1 over that. Or no?
You're going, so we can do the long way where we actually find our inverse and then do the derivative of that. Or you can just remember your formula. And our formula says I just do 1 over my derivative evaluated at this point. This point comes from my inverse. Okay, so you can do the long way of actually finding the inverse and then taking the derivative. Or if you remember your formula, then you can just do 1 over derivative at that point. And this point comes from our inverse. All right, so it says to find the derivative of y inverse at x equal to 9. Okay, so we're trying to find the derivative of our inverse at x equal to 9. So this 9 is on my inverse, so that's my x value of my inverse. Okay, right, so we're doing derivative of our inverse at x equal to 9, so this 9 is on my inverse. So if 9 is the x value of my inverse, what is that in my original? What does x become in my original?
Y.
Your y. Remember, the big idea behind inverse is that you just simply switch x and y. So we're going to use that because to find what's in this box here, I really have to find my original x. Okay. So I want this value, which means I need to find my original x. Okay. So I need to find my original x. So I'm just going to go use my original function. My y value is 9 equals x cubed plus 1. Subtract our 1, we get 8 equals x cubed. What's our x value? 2. So that is what's in my box. So again, that idea that x and y switch, so when we're looking for the y value of our inverse, it's technically really just the x value of our original. Okay, so now we'll just use our formula. In our formula though, we need to do the derivative. So let's go ahead and do our derivative. So y prime equals 3x squared. And we are going to, actually I'm just going to leave it like this for now. Okay, so when I go to do my derivative, so my derivative of y prime, or sorry, y inverse, and this is evaluated at x equal to 9, right? So the derivative of my inverse at x equal to 9. According to my formula, that's just 1 over my derivative, so y prime, at my y value, which is 2. All right, so we did our derivative. Let's evaluate our derivative at 2. What would that give me? 12. So this is just equal to 1 over 12. And that's it. Okay, so again, the key component, really we have to do 2 things. We need to do our derivative and we need to find this y value. Well, this y value is the y value of my inverse, so that's the x value of my original. We had to solve for that and solve for it. So let's do it again with example 3. Okay, so again, every time, and I want you to do this on your homework, is to write original and inverse. just so you don't get yourself confused with the information. We're looking for this box here. Okay, so I'm finding the derivative at x equal to 5. So that's 5 on my inverse. Which is y on my original. Okay, so let's go ahead and plug that in. 5 equals x cubed. That's 5x minus 1. Let's move everything to one side and try to factor. So I get x cubed plus 5x. What would that be? Minus 6 and 0. Can we factor that easily though? No. So they sometimes will throw a problem like this at you, in which you cannot factor easily. Sure, we could do the rational root test, the p over q, and plug those in and check them. Or we can solve by inspection. And so what that is most likely, when we have a problem like this, either 0 is a solution, or 1 is a solution, or negative 1 is a solution. Now, if none of those work, you have to do the PQ test, but I don't know that I've ever seen calculus make you go through the whole PQ test, because that's going to waste too much of your time. So check 0, 1, and negative 1, see if any of those are a solution. 0 is not a solution. Isn't 1 a solution? Okay. So x equal to 1 is a solution. Does negative 1 work? No. Okay, so 1 is a solution. All right. So that's what's going in my box here. All right, so, so that was my root. So that was the solution, x equal to 1, that's what goes in my box. Okay. So again, when we go to do our derivative, so our derivative of my inverse, and we're evaluating at 5, that's just simply 1 over your derivative at our y value. Okay. We need our derivative at 1, so let's go ahead and do that. Should have done that before, and that's okay. My derivative is 3x squared plus 5. I need it at 1. 5 prime of 1. So 3 times 1 squared plus 5. What does that give me? 8. Are we okay? Do you have questions? Alright, so then I'm just plugging that in. So y prime of 1 is 8. So my answer is 1 over 8. Okay, so again, our formula is 1 over the derivative at that y of our inverse. Okay. I want you guys to try. I mean, these are about the same. Go and try example 4. Really the same thing over and over. After example 4, then I want you to go to number 7 on the homework, which is just the next page. Not this one. Okay, do we get 1/5 for example 4? Do we have any questions? Okay, so let's take a look at that number 7 on our homework. So notice here, this is where they did not give us the function. So they gave us a chart of values. So this would be one where you couldn't do the inverse, you couldn't switch x and y just to simply differentiate. Okay, so here they gave us their values, and it says if f inverse is the inverse function of f, find the derivative of f inverse of x equal to -1. So here they've written that notation, f inverse derivative. Alright, so our formula says our f inverse derivative at -1 is equal to, so it's 1 over our derivative at the y value. Alright, we've got to figure out what that y value is. So again, I'm going to go back to original and inverse. Okay, they said at x equal to -1. So on my original, because notice they didn't give me any information about my inverse in the chart, only information about the original and the derivative. So on my original, I want to see where y is -1. I go to y is -1. Okay, what's my x value that goes with it? 0. Okay, so that is going to be the y value that I'm putting in. So I got 0. So I want to evaluate this then at 0. Okay, so this is just 1 over, what's f prime is 0? 4. Right here. 4. Questions with that? So then, write an equation for the line tangent to the graph. Pretty easy. Just what we always do, so we need point slope form. We're going tangent to the graph of our inverse at x equal -1. So we can first have to find our slope at that point. Oh gee, that's what they just had us do. So then when we go to write our equation, y minus y1 equals our slope times x minus x1. Okay, so this is for my inverse, right? That means I need my slope of my inverse, which is the derivative. Slope is that one, 4. And we need the point for my inverse. And my point was -1, 0. So again, it's for my inverse. So -1, 0. So x minus -1, x plus 1. We're done. All right, let's go ahead and go back to in our notes where we had that calculator. It's still the same process, but I want to make sure that we are using the store button to ensure that we do this correctly. Okay, so let's go to example 6. Get out your calculators so you grab one. Yeah. Okay, let me pull up mine while you get yours out. You'll probably beat me to it. Okay. So it says find the derivative of f inverse of x at x equal to 1. So again, original and inverse. Okay, so for my inverse, x is 1. So I need to find where my function equals 1. So 1 equals x cubed minus 4x squared plus 7x minus 1. Don't do this by hand if you don't have to. It's not going to be easy by hand either. So how can I find this intersection? What do I do on my calculator? Graph them and find what? Intersection. So graph 1, graph this equation, find your intersection. This is so much harder to do on the computer. Okay. So when we graph and find our intersection, did yours look like this? Okay. All right, so when we find our intersection, so we get 0.34937081. Okay. If you did not get that, double check your equations. You should have 1 on one side and then x cubed minus 4x squared plus 7x minus. Make sure you use the minus, not the negative side. Okay, so again, anytime you calculate something on your graph, it stores this x value for x. Okay, so if I go to my home screen, if you've done nothing else, you go to your home screen. And so that is now stored as your answer. So if you just hit store, wait, no, hold on, x. Yes, okay, so if you hit x, then that's going to be that decimal that you just found. Okay, so you can leave that as x, you can store it as another alpha value, store it as alpha a, whatever you want. So on your calculator, we have to use that full long decimal. On our paper, though, we're going to actually write out part of it. Okay, so we've got that stored. So we know for our function, for our derivative here, so the derivative of our inverse at x equal to 1 is equal to 1 over our derivative, and that value was what, 0.349? I'm going to write that on here. Now, when we do this on our calculator, though, we're going to actually use the full value. So then on our calculator, I want to do, we want to do our derivative at that point, right? We've got our function already set in here. Mine's in y2. So can I just do my derivative at that using this function here? So I'm going to do my math. Derivative. And I already typed in y2, so I'm going to just go and use my y2. And we want it at the x value we just stored in. You can type that whole thing out if you want. I'm going to type x because I left it stored as x. Again, you can do it alpha a if you want and put a. So it'd be 1 over 4.5712, yada, yada, yada. So let's do 1 divided by that. You could have technically done, oh, sorry. 1 divided by, okay. It's because I'm trying to be fancy. All right, so 1 divided by what we just put in. And do we get 0.21876? Yeah, yeah, yeah. And again, you could have typed it all in 1 divided by and then done your derivative, so on and so forth. So I just want to make sure we remember that when we find an intersection on our graph, that is automatically stored as x. You can rename it if you want, and then we're using that full decimal within here. So our answer then is 0.217. 218, 219, either way. If you're lucky in calculus, you don't have to worry about the rounding there. Yeah, I'm just gonna, either one. I feel like it's better just to cut it off so you don't have wrong. So that's good. Okay, questions with that? Okay, so your homework tonight is twofold. You got that second page of slope fields. Again, only do odds when you have to actually draw the dash marks. And then for our homework in here, just that second page where it says more practice. You don't have to finish the stuff with the pills. Yes. I do. Are there any questions about what our homework is? Guys, we only have 2 more topics left. Don't forget to be working on your When I See I Think packet. Let's do it at the end of the unit.